Thank you. It is wonderful to be back here, and we have a terrific evening ahead of us. And the title of our panel is The Unification of Physics, the Quest for a Theory of Everything, which is shorthand for asking, can physics be unified? Can there really be a theory of everything? And I don't just mean a movie about Stephen Hawking. Should we even try to construct such an all-encompassing theory, or is this kind of a fool's errand, an exercise in asking science to explain more than it really can? I think you all know we are living in a remarkable moment in the history of physics. So much has been discovered in recent years, from dark energy to the Higgs boson, and so many more questions remain. What is dark energy? What is dark matter? Do we live in some sort of multiverse? How do we reconcile the weirdness of quantum reality with the bigger stuff that we see in our everyday lives? And as physics has become more grounded in theory, is it becoming too removed from the empirical world of scientific experiment and testability? So we have a lot of big questions to consider this evening, and we have a terrific panel to help us do it. And let me introduce our speakers. Katherine Freese is a physicist at the University of Michigan. In September, she also became the director of Nordita, the Nordic Institute for Theoretical Physics based in Stockholm. She works on a wide range of topics in theoretical cosmology and astrophysics, among other things. She specializes in dark matter. And she's the author of the new book, The Cosmic Cocktail, 3 parts dark matter. Marcelo Gleiser is a professor of physics and astronomy at Dartmouth College. He's the co-founder of and a regular contributor to NPR's Science and Culture blog, 13.7. He studies cosmic origins and the possibility of life elsewhere in the universe. He's written a number of books, including A Tear at the Edge of the Universe, and most recently, The Island of Knowledge, The Limits of Science, and The Search for Meaning. And Max Tegmark is a physicist at MIT and the scientific director of the Foundational Questions Institute. His scientific interests include measurements of cosmic microwave background and galaxy clustering data, and tests of inflation and gravitation theories. And I have to say, in a remarkable feat of symmetry, like the other panelists here, he has also published a new book this year, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. Welcome, all of you.
Thank you. Thank you.
It's a pleasure. So, Max, let me start with you. When physicists talk about a theory of everything, what do they mean?
Well, we physicists generally see as our quest to try to make sense of this extremely complicated reality that we find ourselves in. And I feel that the 2 most spectacular good ideas that we humans have come up with so far in physics have been, 1, make experiments. In other words, go out and measure a bunch of numbers. And 2, when you have these measured numbers, try to look for mathematical patterns in them. And originally, these ideas worked well only for a very limited aspect of reality, namely the motions of stuff. Archimedes and Galileo and others noticed that everything moved in the same shape when you threw it, a parabola. And later people realized that stuff in the sky always moves in the same shape, ellipses, and parabolas are just little pieces of ellipses, and approximately. And back in those days, if you had Newton here, for example, on stage, right, he could have predicted very accurately for you where the moon is going to be in 100 years or where it was 100 years ago. But he still had no idea about most other aspects of physics, like why the moon has the color that it does, why some things are black and some things are red, why some things are hard and some things are soft. That seemed to be beyond what you could access with this approach. Make experiments and look for mathematical equations. And what we've seen since then is that science has gradually managed to describe more and more of the world around us with the same very approach. James Clerk Maxwell came up with the Maxwell equations, which could describe everything to do with light, for example. Now we understand colors. Schrödinger came up with the Schrödinger equation, which lets us calculate all properties of atoms and why things are soft and other things are hard and why some things actually do look red. And so little by little, this physics approach was able to describe more and more. And the quest for the theory of everything, which is what you're asking me to answer, is simply the quest to complete this job and ask what remaining things are there that we've failed so far to explain.
So why don't we have a theory of everything? What are the main obstacles? And Katie, let me turn to you.
In the universe, there are 4 fundamental forces that we know of, And we understand them mostly. So we understand how electricity and magnetism work. We understand how electrons and protons are attracted to each other and how magnets stick on refrigerators. We also understand, to some degree, the strong force, which is what holds the nuclei together inside your atoms. There's another one, the weak force, which is responsible for a lot of radioactivity and may also be responsible for the dark matter. So those three forces we understand, and even we understand that as you go backwards in the history of the universe gets hotter and hotter as you go back, they unify. And there are theories about how they unify, and accelerators show this unification, at least for electricity, magnetism, and the strong interactions. And we think, and the weak interactions, we think we know how to include also the strong interactions, so we have some ideas how to unify everything in our existence except for gravity. That is a tough one. We don't know a whole lot more than Newton did. You drop an apple, it falls. But we don't have a fundamental understanding, and trying to unify everything, all of the four forces, requires something really radically new. And that's where the unification of quantum mechanics and relativity, you would have to have some kind of theory of quantum gravity to get everything under one unified framework. And that's something Einstein was trying to do.
So is this a matter of we need more experiments, we need more tests, and somehow that'll get us this breakthrough? Or are we talking about something conceptual, some new big idea that we need that we haven't even thought about yet, that will sort of
conceptual? I think we've got people working on string theory, which actually mathematically does unify all the four forces, and yet it's not making predictions for experiment. So let me back up. We need both. We need something conceptual that we can then go and test, and we don't have that.
Marcelo, what's your take on the theory of everything? Should it be the holy grail of physics?
So just to rephrase, so when physicists talk about the theory of everything, they don't mean they're going to predict what you're going to be doing tomorrow morning or anything like that. They really mean, in a very reductionist way, the picture that the world is made of little bits of matter, the elementary particles we call them, supposedly things that you cannot cut down into any smaller pieces. So they are the building blocks of reality, so to speak. And these building blocks of these particles, as Katie was saying, they interact via four forces as far as we know now, right? So when we talk about unifying physics, we talk about creating a description of nature whereby these four forces can be understood as manifestations of a single force. So what we see as electricity, magnetism, or the weak and strong interactions, or even gravity, would, if you put the right glasses on, which means looking at things at extremely high energies, behave as one single force. So that's really the restricted domain, so to speak, of the theory of everything from a physicist's perspective. It's very important that people know that. Now, I wanted to pick something here that Katie said, because she said that, so we have this electromagnetism, which is this beautiful theory that Max also mentioned, that Maxwell developed last century, and Faraday, of course. And then there is this unification, supposedly, with the weak interactions. They're called the electroweak theory, right? And this unification, it's almost a unification. It's not really a unification, because within that theory, you still have components of the two forces there. They don't sort of merge into a single thing. However, the expectation is when you keep going higher energies and further back into the history of the universe, the strong force would eventually join in. So I just want to make sure that it's understood that we do not have that theory yet, right? And in fact, in order for the three forces, the electromagnetic, the weak, and the strong interaction to join, you have to bring into the cocktail, just to use your book thing, you have to bring in something called supersymmetry, which is yet another component, which is a wonderful idea that I'm sure we'll talk a lot about here tonight, that we're still not sure if it's real or not, right? So this unification of these three forces only happens if you call in supersymmetry, as far as we know now, and gravity becomes another thing, another problem, so to speak, at much higher energies.
Yeah, let me jump in here, because my sense is that, so you've given kind of the theory of everything from the perspective of the physicist, and I'm not a physicist, I'm a journalist, and I'm trying to make sense of this. And isn't there really an underlying question here, which is, can science, and specifically, can physics, really come up with foundational laws that explain the universe, that explain the way everything works? Isn't that really the question that we're grappling with here?
I think that's a wonderful question which we honestly don't know the answer yet. And what's the best way to find the answer? Is to try.
Right.
And if we succeed, well then yes, and you're never going to know if it's impossible unless you actually try. The best way to fail in something is to convince yourself that it won't work, and therefore not to try. There is also some difference of opinion in the physics community for how ambitious physics should be, right? You mentioned something everybody agrees with, that the reductionism, looking at the ultimate Lego-like building blocks, that's the minimum of a theory of everything. But you mentioned there are a lot of other things we care about, like that we don't understand today. Like, what about consciousness? Why are you having an experience right now? Why are these 10 to the 28 quarks in this blob here having a subjective experience, while if you just consider this rearranged food that I ate, and put the big blob here, that doesn't have any experience, even though it's the same kind of quarks. Why is that? Some physicists feel that that's not a kind of question that physics should ask. My personal view is that that's also something we don't understand.
Well, maybe you can ask it, but the question is, can physics ever come up with an answer? Can science ever come up with an answer?
My guess is that it actually can. But there are some people who would disagree and say that but it's still a science question. Some people might say the reason that some things are conscious and some aren't is because you need something beyond quarks and electrons. Maybe there's some sort of life force or élan vital or a soul. Then there are people who think, no, it's just a matter of putting the particles together in a very, very special and beautifully complex pattern. Until we try to see if we can actually understand it with just particles, we'll never really make progress. And neuroscientists today are trying very hard to do exactly these kind of things, right? If there actually was some sort of thing beyond physics, which is having an effect on me by pushing my particles around, then if you measure my particles accurately enough, you could see this and study this soul field or whatever it is, just like we looked for the Higgs boson by seeing new forces on the particles. And if we see that actually, no, my quarks are moving just like Katie Freese and Marcelo's equations say that they should move, then there is no outside effect. So I don't think this is beyond what we physicists should at least allow ourselves to think about.
Okay, let's get a response here.
I would say that, well, we told you what the physicist's definition of the theory of everything is. It's reductionist, and we want to explain everything in terms of one single force acting on fundamental objects, whether they particles or strings or membranes. But Max is going farther out there, and I'm going to talk about things that are maybe in between, namely questions that physicists are actively working on now. So even if you were to have this theory of everything, this unification of the forces, we still don't have that's not enough to explain, or is it, the beginning of the universe, the future of the universe. So the evolution of the universe from a very bizarre, what seems to us, initial state, as it expands now, what kicked that off? And so maybe in the search of this theory of the unified force, we get some hints for how to do that. String theory takes us into extra dimensions, and so maybe our universe is a three-dimensional surface sitting inside these dimensions, and these could collide or blah, blah, blah. Who knows? These are very, very interesting ideas. And so this is a notch down from understanding consciousness, but still very interesting, fun problems. The arrow of time, these are tough ones, but we are actively trying to pursue these. In fact, two of us were on a panel here on the arrow of time. So that's an interesting.
Well, I just want to follow up on something you said. You're saying that even if we come up with sort of a more sophisticated view of these various forces of nature, that's not going to get us back to the very first moment of the Big Bang? It stops before then?
So this ties into what Marcelo was saying. So in accelerators now, we see the unification of electromagnetism and weak interactions. And maybe we could someday build a really, really, really giant one and see the unification of the forces. And that would take us, in principle, the higher energies correspond to the higher temperatures of the Big Bang. And so I don't know if in answering these questions we'll answer what happened before that. So these questions are definitely related.
Yeah, and we've been getting by quite successfully with a sort of schizophrenic swindle, as it were, in physics, where for some problems, we can just ignore gravity and calculate everything wonderfully with quantum field theory and predict what's going to happen at the Large Hadron Collider, and it works great. That basically works for everything really small. And then for other problems, we can ignore quantum mechanics and do general relativity theory, and it works great for black holes and large things in our universe. But then there are some pesky problems, very few. But for example, the origin of our universe is one. Well, you actually need both. You obviously need general relativity because things are very heavy. Right? We're talking about our whole universe here, and things are obviously very small when you run time backwards and everything is scrunched together. So to figure out what really happened, you actually need to use both theories at the same time. And to do that, we have to do what both Marcelo and Katie said, and actually find a consistent mathematical theory which incorporates all of this consistently. And I, for one, do not think that this is a problem with nature. I think it's a problem with us and our understanding. I think nature knows exactly what it's doing and how it's supposed to evolve from one day to the next. And the reason that our two theories don't talk to each other is because we haven't yet found the correct description.
That's why you're asking. I think conceptual is, there's more to.
There is a fundamental problem, though, with this, since this is a little bit philosophical here, right? So it's the problem with this constructing a physical theory that describes the origin of the universe, right? I mean, so just a tiny bit of history here. This is one of the oldest, well, religious, right, questions, because lots of different religions in the whole world and throughout history came up with some narrative of creation, the creation myths, right? And there are lots of them. We know of a few are very popular in the West, but they're
We
not
have the
the
best
only
one, the Big Bang.
Right. And that's, you don't want to call it a creation myth, do you? That won't get you a grant. But the point, though, is that what has happened is that there is an issue in philosophy which is called the problem of the first cause, right? And philosophers have gone around this by usually kind of bringing into the game something which is not cause. So the idea is this, like we're all here sitting here tonight, right? But then you start asking, well, while I'm here, well, because I signed up. And then you start, well, when was that? Well, I was doing this, and that was my birthday. My parents were born, my grandparents, and blah, 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 blah. If you keep asking questions backwards, you go to the beginning, to the first cause, the cause that started all the causes, which in our case, we call it the initial conditions, right, of the Big Bang, so to speak. So this is something that, for example, Aristotle was worried about, right? So he came up with this notion called the unmoved mover. So the unmoved mover was the entity that could move without moving. So it was a deity, some sort of divine force there that would impact motion in his cosmos from the outside in. And the problem is that we have been dealing with this issue of first cause forever, right? And cosmology, modern cosmology, made this question scientific. We now have actually a scientific way of asking this question. Can we come up with a model where we can describe the beginning of the universe? And people have done that, right? There are several different kinds of boundary conditions, meaning the beginning of everything started with some assumption that can trigger the universe, right? Out of nothing, and this nothing is extremely qualified. If you're here in the first debate, I hope people talked about that. There is no such thing as nothing in physics, right? But the point I'm trying to make is that even if you come up with a theory, a physical theory that describes the beginning of the universe, that theory was built upon a whole conceptual framework, energy, conservation laws, maybe general relativity and quantum physics. And these theories are taken for granted in order for us to begin to be able to talk about something.
Well, let me just see if I understand. Are you suggesting that this modern scientific effort to explain everything is basically a new version of what religious thinkers used to do? Is this just sort of religion 2.0 in the guise of physics?
I love that. Well, in a certain sense, yes, with a very fundamental difference, right? The very fundamental, I mean, the impetus to try to understand everything and to explain everything is very human, right? And I think the reason why people buy more books about cosmology than about laser physics is because we want to understand, we want to share this knowledge somehow, right? But the difference essentially is what Katie was talking about before, which is testability. Actually, you said that, experiments. First thing, greatest idea. So in physics, ultimately, nature is the judge. You can come up with any crazy idea you want. If it is confirmed by a series of experiments and it can be reproducible, then we rubber stamp and say, yeah, this is good, as long as it doesn't get broken down later on.
So Max, do you see a connection between the religious impulse and the scientific
I
impulse?
completely agree with Marcelo that the basic impetus for asking all these questions, which led to the creation myths and all these great religious stories, was of course the same very curiosity that makes every kid want to think about these things, and that's the scientific spirit. I think the key difference is what you said so nicely there, and the way I would put it is, as a scientist, it's better to have questions that you can't answer than to have answers that you can't question.
Good.
And
a good one.
well, we are allowed to question everything. That's very much the point of science. And coming back to your question about the part about the unmoved mover, there's always been questions we couldn't answer in science. There's always been a frontier of our knowledge, right? Some distance away, we didn't know what was farther. Then we explored more. We found that we live in a solar system, in a galaxy, etc. Similarly, there was a frontier of our knowledge in time. Isaac Newton, he could figure out, again, as I mentioned, where planets were 100 years ago, but he had no idea what made the planets. And we shouldn't sit here and be smart Alex and lampoon religious people 1,000 years ago who thought the best explanation was that someone made the planets, because that was the most plausible explanation available at the time, right? Now, when you can simulate in your computer what happens when you put in a gas cloud and gravity makes the planet, we feel we understand where they came from. But then where did the gas cloud come from? And now, in cosmology, we also know that if you just start with something, everything we see here around us in our universe with our telescope, squished together into an extremely dense and hot state, so it's hotter than the core of the sun, flying apart so fast it doubled its size in under a second. That will, when we simulate it carefully in our computers, evolve into everything we see around here. So we've pushed the frontier of our knowledge now back to a second, and if the theory of inflation turns out to be correct, which we will have to wait and see, we will have pushed our frontier back maybe to the first hundredth of a trillionth of a trillionth of a trillionth of a second, which is progress, but that's still not the very beginning. And finally, is there an unmoved mover that started it all? Well, maybe not, because we've discovered also that a lot of things we thought were fundamental, like the continuum nature of the water that I was just drinking here, that it's actually made out of some fundamental building blocks. It's actually kind of grainy. It's made of these water molecules. We're starting to suspect that actually it's probably the same way with space, maybe even with space and time, that it's actually ultimately not continuous and made out of some quantum building blocks of some sort. And it might very well be, as it is in some of this early wave function stuff that Marcelo mentioned, that if you go really far back, time as we know it doesn't exist anymore. There is some sort of quantum fuzz where time doesn't really have any meaning. And then we actually, that beautifully gets us off the hook. Because you can't ask what caused it, what happened before, if there was no before.
Well, I mean, there's also this problem of what the beginning is. Now, you've said, well, we have our modern creation myth, maybe myth is not the right word, it's the Big Bang.
Creation narrative.
Creation narrative, okay.
I'm going to, this is a slight shift of subject to the human worldview. Mm-hmm. So 100 years ago, Albert Einstein was writing down the theories of relativity. They were being tested. And yet, on the observational side, scientists thought that every star out there is part of one galaxy, the Milky Way galaxy. So our knowledge of the universe from an observational point of view was extremely limited. So then that was resolved in 1929. Edwin Hubble, the same guy who discovered that the universe is expanding, proved basically that things are too far away, there have to be other galaxies. And so if you fast forward 100 years, the stupendous improvements in our knowledge of cosmology, and what I'm talking about has nothing to do with religion, but it sure affects our worldview. So back in the day when we used to think we were at the center of the universe, and then the church didn't like that, took a while to accept that the sun was at the center. then there's not just one galaxy. There are these, they thought there were island universes, that there's galaxies and galaxies, that we don't know how many, probably an infinite number. And yet, the amount that we know has gotten so huge that there's something we call the edge of the observable universe, the horizon, and that's as far out as anything can come from that we'll see. Light takes a while to get to us. So 14 billion light years away, that's the distance beyond which nothing can have reached us in the age of the universe.
So it's possible that there could be other stuff further away, but we'll never know because we
Well,
can't
but
see
the point,
that far.
but the point,
Unless you wait
the point I was going to
a long
make
time.
is that we have it down. We've got everything. We don't know what dark matter and dark energy are, but we pretty much have an understanding of the basic physics all the way out to the edge of the observable universe. So, do I feel small, a little grain of sand? Well, yeah, but I feel like, whoa, our brains are pretty big. So our understanding is absolutely enormous. So it's not really about religion, but it's about the level of understanding that we have.
I want to ask, there's a famous quote from Steven Weinberg. He said years ago, the more the universe seems comprehensible, the more it also seems pointless. What do you think?
I'll leave that one.
I very strongly disagree with that pessimistic spirit. I think that if we've learned anything by studying the cosmos, it's that we shouldn't be looking. It's not that our universe gives meaning to us. We give meaning to our universe. Raise your hand if you think galaxies are beautiful. Okay, why are they beautiful? They're beautiful because some people with telescopes looked at them and took pictures, and the people who are conscious perceive them and behold them. That's what gives them their beauty. If there wasn't any conscious being in our universe at all with telescopes, these galaxies would not be beautiful. They would just be a giant waste of space, as far as I'm concerned. So I think it's completely silly for people to get an inferiority complex just because we weigh less than a galaxy or take up fewer cubic feet than a galaxy and say, oh, we're so small. It's the fact that your brains are the most remarkably, beautifully complex structures in our universe. The fact that your brains can be conscious of all this magnificent beauty out there, it's the whole point of the whole thing.
So, Marcelo,
that's where the meaning comes from.
I agree 100%, but I think what Weinberg was really talking about was that he just meant that the more we understand the universe, the less purpose there seems to be in the universe. So there is no grand designer behind the scenes. The universe just happens to evolve in different ways, and there is just a bunch of accidents to create eventually us. I think that's what he meant by it. So the point, I'm interpreting his words, the point is that there was no point, right? There is no, we're here just because it so happens that in this little planet, the conditions were such for life to evolve, right? And there was a whole big history about that. And what is really remarkable is that the transitions that life had to go through from, first of all, the jump from no life to life, right? From non-living chemistry to living chemistry. It's like a huge mystery, and it's a remarkable, now a scientific question as well.
Right.
There are lots of people trying to figure that out. How on earth do you get atoms, right, to combine into molecules, and somehow this group of molecules begin to behave as a living organism in the sense that it can feed from the environment, it can mostly reproduce. So this jump from non-living to living is amazing. But then that's just the beginning of the story, right? Because then you go to unicellular with a nucleus with the DNA protected, right? So then it becomes a little more complex unicellular. Then you go to multicellular organisms. And each one of these jumps in the history of life is tremendously complex and improbable.
So what does that mean for you in terms of?
Well, we're getting there.
Well, I mean, to cite
I was going to tell the whole story.
Well, I'm going to speed you up a little bit here to cite the subtitle of your book. I mean, the search for meaning. So, I mean, what does this have to do with we as humans, who are, in the grand scheme of things, would seem to be a rather insignificant speck in the cosmos, but does this help in the search for meaning? Knowing this?
Absolutely. This is just what you said. It's because we are this remarkable molecular machine that has self-awareness, right? And that's just unbelievable. So, we always talk about the Copernicanism in science, which basically means that the more we learn about the universe, the less important we become, right? The idea that first we're the center of everything, and then the sun became the center, but then there was one galaxy, but then there were many galaxies, and the universe is expanding. and now we're not even made of the most important thing. I mean, it's one indignation after another, right? So it's like, what is the point of all this? It's like this, it's very depressing. However, when you look at it, no, that's how most people think of this, and there is a lot of anguish about this that says that we are really worth nothing, and the point is precisely the opposite, that because we are these molecular machines capable of self-awareness, capable of thinking, we have a very fundamental role in the universe, which is to create meaning to it, right? And so I actually call this human centrism, the idea that we humans are actually, in a metaphorical sense, obviously, the center of the universe right now, because as far as we know, even if there are other intelligences out there, they are so far removed that we are it. And because we are it, everything that we do has tremendous meaning to our existence, And as Neil deGrasse Tyson likes to say, you have to shake people around the streets, to tell them that you're made of stardust that can think, right? And so that, to me, is truly remarkable. And that's where you begin to find meaning.
So, Katie, what about you? Where do you look for meaning? Or do you look for meaning in this world of physics?
So I guess in response to what we've been talking about, I think what I was getting at earlier, that not only are we remarkable, but we understand most of it that's out there. So we don't have to be afraid. There's no bizarre thing that's going to happen and attack us because it's too far out there. So we have some, as opposed to, I guess in the Middle Ages, there's Bergman movies about people going into the woods and there's winds blowing, and those, of course, are gods. So I think we're better off. So we have less. Our self-awareness has improved, has only grown.
Your mic just went off there.
Well, I don't know what to do about
there
that.
it is. Back. Okay.
That's theoretical physics.
But the idea that we are the best thing out there, I think, is hubris. I don't know that. There could be plenty of intelligent species that fly along, look at us, we're ants, we're uninterested, and let's hope that the juveniles don't take an interest and squash us for fun.
I think it's interesting to combine the optimism in Marcello's words with the optimism in Katie's words here also, because you pointed out very eloquently here that it's not just that we've discovered that our cosmos is much larger than we thought. We hadn't just underestimated the size of our cosmos, finding that we're part of a solar system, in a galaxy, in a vast universe, etc. But we also really underestimated the power of our human minds to understand our cosmos. And that, I think, is an incredibly inspiring idea. And if you combine that with what Marcello said, that we create meaning in our universe, it's very important when you put these two together to realize that contrary to what we were taught throughout much of human history, that this is it, this is as good as it gets, that's not what the laws of physics say. There's absolutely nothing in the laws of physics that says that you can't rearrange quarks into an even more amazingly flourishing society than this, right? Here on Earth or even beyond.
Wait, what are you suggesting?
I'm suggesting that, as we heard here from Marcello, and from Katie, we've come a very long way from no life to more and more complex life to here, right? We have billions of years left.
Are you?
And
He's talking about Terminator. No, I'm kidding.
No, I'm going to say some optimistic things. I'm just saying that it's quite possible in the future life can flourish even more than it is now here on Earth, and maybe even in much of our observable universe. And if that all started here, that's absolutely nothing for you guys to feel insignificant about, right? I think it's extremely significant what we do. Well, in fact, I also feel we've reached kind of a fork in the road right now where we have, you brought up technologies that we're inventing that are so powerful that we can wipe ourselves out with them. We have technologies also that can make things much better. All this knowledge that you talked about that we've discovered helps us not only understand, but it helps us, in principle, make things better, right? So we're at sort of this fork in the road where if we get our act together and don't do stupid things, we can create even more meaning. And I think that's a very inspiring challenge to rise to.
Marcelo, you're going to jump in?
Yeah, I was just going to say that this realization of our uniqueness in the grand scheme of things and how rare our planet is, right? Now we're looking for other Earths out there, right? And there may be other Earths out there, right? We're looking for them, and maybe We're going to find something. But the point is that right now we are here and we are stuck here. And what we have found is that this planet is truly unique in many, many ways, right? It's not just that it has water and it's warm. It's about its magnetic field. It's about the plate tectonics. It's about the mass of the moon. All these different factors contribute to making Earth a beautiful place for life, not just to exist, but to exist for a very long time so that it has time to evolve into more complex.
So I'm just reading about this, and I'm not an expert on Mars, but I'm understanding that they're now saying from the latest probes, the Curiosity, that there may have been water there for billions of years, and the comets are bringing organic molecules, so past life. I'm not talking about now. No, that's right. I don't know. Nobody knows why it got wiped out, why Mars got so desiccated. But so even Mars might have had intelligent life. My God.
No,
Well,
nobody's saying that.
It's pretty clear that they never invented the internet on Mars.
Yeah, no, that's
I think
not.
I agree with your point, Marcelo, here that even if there are other intelligent life forms out there who are more advanced than us, it's very, very possible that they're very far away. You know, if you have a kid and you give them 1,000 toys, they're going to get really spoiled and not take good care of them because they'll be like, oh, if I break this one, I can always get a new one from daddy or whatever, right? We should not treat our planet that way. And we should not take for granted just because we saw it on Star Trek that there are all these other civilizations that are out there are going to keep the meaning going in our universe if we mess up. I think
That's what I was
my
trying to
takeaway
get
from
at.
what Marcelo is
Yes.
saying is I think we're saying the same thing here, right?
Yeah.
That we really should be very grateful for the amazing planet we have here and really, really be good stewards of it. And I think, honestly, we're doing a terrible job.
No, but I am disagreeing. I'm saying that I think that it's very likely that even in our own galaxy it seems like every sun has a solar system around it, every star, not at least half the stars. And some of those are looking pretty good for life as we know it, not something Star Trek-y. Well,
That's absolutely
But,
not
so
non-carbon based.
So I think even in this galaxy that it's likely that there is life as intelligent as we are.
Okay, I'm going to
So
do a
I think
little.
we would disagree.
I'm going to do a little quiz here. So you think there's intelligent life elsewhere? What about the two of you?
It's a completely unanswerable question to us.
What's your hunch?
So let's be very precise here. So the fact that there could be life
Carbon-based.
elsewhere, carbon-based,
Carbon-based.
all like with similar things that we're used to, is highly probable that there is some sort of microbial life elsewhere, just because of the sheer number or the Earth-like planets. So I'm being very sort of Earth-centric in a sense, right? Intelligent life is a completely different ballgame. And because of all these little hoops that you have to go through to go from an amoeba-based thing to what we are, right? And so just to give you an example, and this is really important because the dinosaurs, they were here for 150 million years, and they were pretty stupid, right? I mean, they didn't build radio telescopes, right? But they were happy, they were fine. And the reason why they were extinct, I don't know if you've seen a cartoon, is because they were smoking too much. No, but the reason is because that asteroid came, 65 million years ago, it hit the Yucatan Peninsula in Mexico and wiped out all the cold-blooded reptiles, etc. The point is that evolution does not necessarily lead to intelligence. Evolution is about adaptation, is about being okay in your environment. So it's not like you plant life somewhere, you wait long enough, and out pops an intelligent creature.
I don't know. The smart ones win. So
They win,
we
but
are
the dinosaurs...
speculating here. We are
No,
speculating
not
here.
necessarily. I'm not, actually. The dinosaurs, this is evolution theory. It's natural selection. All you need to survive is to be, to have a hierarchy where whoever is better adapted survives until there is a major cataclysm and where the whole soup gets kind of mixed up, so to speak, right? It's called the, how's it called? That you have these punctuated equilibrium idea, right? That you have like cataclysms, things change, stabilize, they have another one, etc. And so it's not necessary that life leads to intelligence. That's a very important point.
So Max, what's your best guess?
Yeah, my best guess is I might be the most extreme on the opposite side of you, which is
Jeez.
perfect. I'm sitting on the opposite side of you.
No.
And that I actually, my guess is that the nearest planet where there is something as advanced as the New York Academy of Sciences evening discussion going on, is so far away that it's even outside of our observable universe, so it doesn't matter for us. Wow. That's my guess. And the reason I'm guessing that is because, well, I first agree with all the things you said, that there is absolutely nothing automatic about you start with an amoeba and then you get the internet after a certain amount of time. Well, we shouldn't laugh at the dinosaurs for being losers, for going extinct, right? Because we haven't been around for 150 million years. We've been around for 150,000 years, tops. And moreover, there's the famous Fermi paradox, where when Enrico Fermi first pointed this out, he said, well, if it's so inevitable that you get life, and it's pretty easy to invent spaceships and stuff and colonize, well, since no one is here, the nearest neighbor is probably pretty far away. Well, guess what? That paradox has gotten way, way worse in the last 5 years, as we've discovered that there are actually billions of planets in our galaxy even, that are pretty Earth-like, which, as you mentioned. Mm-hmm. And many of them are 2 billion years older than our planet. So if it's so automatic that you get advanced life, then that means there would be a lot of those civilizations pretty nearby in our galaxy, which have had 2 billion years of R&D to get over here, and they still haven't. So my guess is that actually the nearest neighbors are probably outside of our observable universe, and if we want there to be meaning in the part of space that we know exists, it's up to us.
We've been talking about
Okay.
mysteries, the big mysteries in physics, the big mysteries in science. And I'm sort of curious about if each of you could pick like the biggest mystery, the thing that you're most curious about, that you'd most like to get an answer to, what would it be? Marcelo?
To me, the biggest mystery is the origin of time. How things got started. And I honestly don't even know if we can provide a fully scientific answer to the question, simply because of the way science works. Science operates within a conceptual framework, and any answer that we give uses that framework. So the question then becomes, where did this framework for science come from? And how is science even going to deal with that, right? So we're really kind of stuck with that sort of paradox. So that to me is the hardest question you can ask.
Katie, what about you?
There's a lot of good ones, but the one that has occupied me is, what is the universe made of? So if you take everything in this room, your body, the air, the walls, now let's throw in the planets, throw in the stars, everything that we know about in our experience is made of atoms, but all of that adds up to only 5% of the content of the universe. Well, I want to know about the dark matter and the dark energy that make up the rest, the other 90, the bulk of our universe.
And you think, I've been reading your book, you think that we might have an answer relatively soon to dark matter, at least.
Yeah, so 25% of this cosmic cocktail is dark matter, and that's what makes up, for example, most of our galaxy. So the Milky Way has this flattened central region. It's like a pinwheel, and if you go out along one of them, you get to the sun. That's where all the stars are. But then there's this giant spherical object that we call a halo made of dark matter. We think it's some new kind of fundamental particle. We think it might have the weak interactions that I was talking about before, which means you can go build detectors underground, wait for them to be hit by these dark matter particles, and people are doing that, and there's a number of experiments that are seeing something, and they're in disagreement with one another, and so we have to wait and see. But I think the community at large, this is a problem that's well defined, soluble, and there's a good chance we'll have this one in the next decade.
Max, what's your biggest mystery?
I first of all agree with you that there are a lot of good ones here to pick from,
Yeah.
and you both picked good ones that I'm very excited about. So let me pick a third one. I'm fascinated by that, which is the physics of consciousness. This is something which philosophers have pondered for thousands of years. It seemed for thousands of years like a pretty hopeless problem that you can speculate about over some alcoholic beverage and then go home because there's nothing you can do about it. And the reason people kept thinking it was hopeless was because you have privileged access to your own conscious experience. You know you are aware of these things subjectively and that you're experiencing these colors and sounds, right? But for most of human history, nobody else could know what you were thinking about. But that's changing now. We have this revolution in neuroimaging technology where you can put yourself in an fMRI machine or a magnetoencephalography machine, or you have a lot of experiments with epileptic patients with a lot of electrodes in their head while they're fully alert and talking and doing stuff. And by just looking at that data and plugging it into a computer, you can figure out in real time a lot of things about what they're actually thinking and experiencing. You can show them pictures, and then the computer can say, that was Halle Berry you're thinking about. And they go, yes, how did you know that? And what's so cool about that is it takes this old metaphysical thing which seemed kind of hopeless, much like cosmology thought seemed hopeless.
I have to tell you, my son has a crush on Halle Berry.
How do you find out? So what I think is so exciting about this is, you were excited about dark matter because there's a potential to actually do something concrete about it. And I'm excited about this for the same reason, because if you put yourself in a scanner, which is observing from the outside all the information processing that the computer in your head is doing, right? And then you can, at the same time, observe subjectively from the inside what of this information processing you're conscious of. You can compare the two.
But the
and you can
problem
start
is
to see,
that doesn't explain causation.
Well, I was going to
I mean,
get
that
that.
doesn't. I mean, yes, you
Let me
could
get to that.
you could match, with the brain imaging and the thoughts, but it doesn't explain why those thoughts.
Well,
pop
let me
into our
get to
mind.
that. Because in physics, first of all, we're not mainly focused on the why question. Right? We're very interested in how. And if you could have said the same. If you want to know what is a fire, it's just some arrangement of atoms. Well, you try this arrangement, that's not fire, or this one is, and then you look for patterns, and you say, whenever these equations are obeyed, that's what we call a fire. You see a pattern, right? And we can start to do something similar here. David Chalmers, who's moving to New York now, right, articulated your question famously as the hard problem of consciousness. He said, why is it that you put a quark blob together and there's a subjective experience in it sometimes, but not other times? From a physics perspective, from our perspective, you can transform that instead by saying you start not with a hard question, but with a hard fact that some quark blobs are conscious, like this one. Hope you don't feel offended by being called a blob, okay? And some are not, like the food you ate. And then you can say, okay, what is it that's different about those patterns? And what I was getting at with all the neuroimaging is you can start to look, okay, of all the information you can measure from outside is flying around in your head, which of that information is the part that you're conscious of? And which of that are you not conscious of, like what's controlling your heartbeat and a gazillion other things? And then you can start looking, what is it that's so special about the conscious part? What equations does it obey? Is there some simple idea? Is there some pattern here? Is there some principle? And my gut tells me there is some principle there to be discovered, that there's a certain kind of complexity of information processing, which is the kind of, my guess is that basically information is the way, the conscious subjective experience is the way information feels when it's being processed in certain complex ways. And I think we now are on the verge of being able to scientifically ask, what are those complex ways? So that's a question I'm very excited about.
Marcelo, I have to turn to you because I know you have also written about science and consciousness. Do you agree? Do you think physics will crack the consciousness problem at some point?
I don't, but I admire Max's optimism. I think that's the spirit.
Just to add to that, I mean, and the same with dark matter hunt and understanding the origin of our cosmos. You don't have to be 100% sure you're going to succeed to really want to try, right? We all agree that the best recipe for failure in any endeavor in life is to convince yourself that this is impossible and therefore not to try. You just have to feel you have a good shot at it, and then we try our best.
But there's another way, there's another approach, because we're really talking about, when we're asking, how much can science explain our world, our universe that we live in? The other conclusion that the other guess that you might put forward is, science can take us pretty far, but there will always be some things about our world that science just will never be able to explain.
Right.
That's right. But there have been so many people.
Well, that's good. That's what keeps us employed.
I don't think we're going to run out of mysteries anytime soon, so I wouldn't worry about our paychecks. But look in history. There have been so many times when famous physicists stood up and said, physics is basically over. You know, there are all these things, you can never figure this out. You know, you know so many stories. I'll just mention one of them. The famous physicist Ernest Rutherford, one of the greatest atomic physicists ever, said in the 1930s that we're, you know, nuclear energy, just a bunch of moonshine, you know, it's never going to work. That was only about a decade until nuclear weapons, nuclear reactors, and so on. So whenever someone says this is impossible, I say I see an opportunity.
So Marcelo, you have written exactly on this question.
Yeah, so I think, again, I admire Max's optimism, no? But the point being the following: I think that's totally true. We have to obviously pursue those, but we also have to be aware of El Dorado, you know, sort of like the fabled city of gold. And there is a difference between pursuing El Dorado because you believe El Dorado exists, or just learning as you try to find it. You know, and so, and I think that's a very important distinction, because we have to go back to how we humans make sense of reality, right? And we make sense of reality by measuring it.
Yeah.
And the way we measure things is always limited by the technologies that we have at our disposal, right? We can only see so far, we can only see so small because of our telescopes and our particle accelerators, which are basically glorified microscopes. And what we have seen through the last 3 or 4 centuries have changed dramatically because of this big evolution in our technologies, you know, of instrumentation. And that's always going to be true. I mean, I think that technology is going to keep evolving. We're going to keep seeing more and more. However, we can never see everything there is to see, just because of this myopic nature of how we acquire knowledge of reality. Now, that's not necessarily a bad thing. You know, I mean, I think we will keep on seeing, but to have the hope that we will be able to encompass all of reality through our knowledge is, I think, against the whole way in which we do physics. We pursue knowledge in nature, you know, through our acquisition of knowledge with our tools and our intuitions, of course. So, for example, just to go back to your main theme, you know, the theories of everything, right? So when people talk about the 4 forces of nature and this is our theory of everything, I think we have to be very careful about that, because it is very possible that 50 years from now, 20 years from now, 100 years from now, there'll be another force. So there'll be a completely different effect.
Well, in the subject of dark energy, people are playing around with the potential for a 5th force.
There you go.
Yeah.
So you have to be careful. This would be a theory of everything given what we know now, not a final theory. You know, the idea of final absolute truth in the pursuit of knowledge in nature is, to me, a fallacy. In fact, it's called the Ionian fallacy, just because of the first philosophers, the guys that wanted to understand exactly what you said. I want to know what the universe is made of. You know, that is the first philosophical question ever made by Thales. You know, 650 years, you know, BCE, he says, I want to know what the world is made of. And his theory of everything was the world is made of water.
And actually, it's interesting, all 3 of us picked our answer to your question using exactly the same method, if you think about it. We all looked around us, what is it we still don't understand? We looked at the list of all the cool big things, and then we asked, out of these things, we whittled it down by each picking one of those things for which there was a revolution in new data coming. You picked the origin of our universe because we're getting all this spectacular data in particle physics and in cosmology with the Planck satellite, etc. You picked what's our universe made of because there's this revolution in new data for looking for dark matter in various ways. I picked consciousness because there's a revolution of data coming in neuroscience.
You know, I wanted to say something about the experience of being a scientist. We really get to have fun. We are at the forefront of technology. That means we get to make stuff up. We invent stuff. And then we hope, at least from the point of view of a theorist, we hope that those experiments are going to come along very soon, and we hope the nature matches our ideas. The odds are that what we're doing, it may be well motivated, we may be doing the math correctly, we're doing nothing wrong, but nature just doesn't work that way, in which case I may have spent most of my life on science fiction. But so this question, so predicting what'll come in the future is awfully difficult when new data comes in and all of a sudden, zoop, paradigm changes. You got to ask different questions. head in a different direction.
We need to bring our audience into this discussion. I'm willing to bet there might be some questions or comments in response to all of this. So if you could please raise your hands. There are a couple of roving mics.
So I think you're conflating the use of quantum mechanics and the interpretation of quantum mechanics, and so you can spend your whole professional life as a physicist using quantum mechanics all the time with tremendous success, and we have all our digital gadgets to prove it, without having a clue what it really means, and there is indeed a very big challenge there in the interpretation of quantum mechanics, but all the theories that we use to describe the fundamental forces of nature, which we call quantum field theories, which is sort of like the scary topic when you're a grad student and you have to take the course. And you're only really learning when you teach it, I guess. But anyways, is that those theories are very, very functional. They talk about the probabilities that you're referring to, but in a very concrete way, and we don't really worry so much about the interpretation of quantum mechanics as I think But yes, understanding quantum mechanics, so even what no locality means in physics is still pretty much an open question.
And just wanted to add to that there certainly are a lot of people have thought a lot about the questions you ask, because it's not the case that it's something being ignored. And there is a wide spectrum of views and interpretations of quantum mechanics, and some I talk a lot about that, for example, in my book, and there are some different versions of this which even make different predictions for whether, for example, quantum computers in the future will work or not. So this is a very exciting field which even connects to some things we can test.
I guess the one thing I would disagree with is the statement that we're not experimentally testing quantum mechanics. I mean, remove transistors are based on quantum mechanics. So I mean, let's just shut off all electronics in here, please, right away, because otherwise it relies on quantum mechanics. So this I guess gets back at what you're saying. There's fundamental, very difficult questions that people do work on, but we're just not we're not those people.
Yeah. So glad you brought this up. There's a lot of wonderfully elegant work you're referring to there. I don't see reductionism and emergent phenomena as in any way being incompatible with one another. Often we discover the emergent phenomena first before we have a clue what they're emerging from. We discovered the Navier-Stokes equation that describes the motion of water before we knew that it was made of water molecules, and before we knew that there were quarks, right? Later on, when we understood quantum field theory, we can derive from this that there's a solution to it corresponding to water, and then it's going to obey the Navier-Stokes equation, and we have this beautiful emergence. And then later on, when we study the water, we can forget about the quarks in good conscience, because we know that we don't need to worry about what these water waves are made out of to study the wave behavior, right? Same thing with Boltzmann's work. Now you can derive all of statistical mechanics from quantum statistical mechanics and grounded in quantum field theory. That's not the way historically it happened, but in the end we see that it all hangs together beautifully, that everything is resting on these very solidly on these reductionist principles, but in our everyday life it's very convenient to just look at the emergent phenomena and the rules they behave. I mean, when you speak with one of your friends and you think they look a little bit sad and you wonder what might have happened, you don't need to go back to thinking about what their quirks were doing yesterday, right? You think of higher level phenomena, and that's quite fine. Back to you.
No, I can answer that. So depends where you want to go. A B-2 bomber costs about $2 billion. So how many B-2 bombers do you need to guarantee the safety of a country? And so it's really a matter of...
You ordered 46.
There you go. That's a lot of particle accelerators right there. So I think that yes, science does become more expensive as we go by, just because the technology becomes more complex and bigger. But that does not mean that we should stop asking these questions, because for sure, if we stop asking these questions, we'll stagnate, one, as a species, and we won't be able to build the B-3 bomber.
Just to add to that also, we have to remember that there is also a lot of science you can do without building CERN or very expensive facilities. For example, there was a recent Nobel Prize for the discovery of graphene, a single layer of carbon. When Geim discovered this, he had very, very expensive lab equipment. Right? He had a lead pencil and Scotch tape. That's it.
So I'm gonna make the point. CERN. What is the biggest societal impact of that, and was that worth it? And now you know the answer, but don't give it away right away. So there were all these physicists that went to Geneva and they took data, but they had to go home and teach. They had to go home to their families, and they still wanted to see that data. Well, so a computer scientist named Tim Berners-Lee did something absolutely brilliant, and he created the World Wide Web. So that $10 billion, actually at that point it was less, that went into CERN. Was that worth it? Has that changed your life? Yes. I challenge you to go through a day without it.
There's another question that comes out of this question, which is, are we at the point in science, especially in physics, where we need all of this technology? We need despite the example that you just gave, but for the big conceptual breakthroughs, have we left the era where the Einstein, the solitary genius could, totally revolutionize our thinking just within this one man's head?
No.
I don't think so.
Yeah, we need them.
Yeah.
We need them.
You can still have theorists which are sort of lone wolves and come up with great ideas, but then you have to test them.
Dark energy might need this. The theory of everything might need someone of this caliber.
So it's different, right? Because the difference being that when Einstein came up with his theory 100 years ago, the tests for the theory, at least the bending of starlight, just took a bunch of astronomers and some telescopes, and it didn't take billions of dollars. Now, if you come up with some revolutionary theory, in fundamental science, meaning very high energy physics or something like that, probably we will take big equipment or some very precise underground detectors to find that, and that is sort of inevitable.
Oh, they're actually cheap. The entire U.S. budget until recently was $2 million a year for dark matter experiments.
So some fundamental research is not expensive, right?
Yeah, and the entire American budget from the National Science Foundation for all of physics, and throw in math too for good measure, is four of those bombers per year. So I think the most important piece of lab equipment actually we need to invest in for this is our children. Because I agree there's plenty of a role for brilliant minds to come and do things. And I think
especially your daughters.
There you go.
Yes, high five. and because of that, it's wonderful that the New York Academy of Science is doing its share to get people fired up about science, to get our kids fired up about science. We live in a country right now where 46% of the population in a recent poll think that our universe is and Earth is less than 10,000 years old. Now, that is not the kind of thing our daughters need to hear, especially not from their school teachers, when we want to inspire them to go and do science. We live also in a society where it's very fashionable for whenever some scientists say something which some powerful person doesn't want to hear, they just dismiss the science and say the scientists are losers, and that's also not something we want our daughters to hear, or our sons, if we want to inspire them to go and be the people who are going to solve dark energy in the future. So let's keep inspiring our kids.
Well, there are theories of quantum gravity that treat the wave function of the gravitational field. There is a whole tradition of that dates back to the early 60s even, where you can write something called the wave function of the universe, and where you try to quantize gravity in that way. And then there is a whole other approach, which is a more recent one, called loop quantum gravity, where you basically break down space into little chunks, which are basically fluctuations of the metric, which is what you measure, to distances and times frames. So yes, people have been trying to do that, and they've been partially successful.
Just to add to that also, all the questions you're asking, can certainly be tackled. And yes, there is a problem with getting good experimental data on it because you need to do extremely violent things to the fabric of space-time for these effects to become strong. So to learn more about them from nature, we have to, since we can't do such violent things with our technology, look at the most violent places in nature. That's why it's so interesting to look really hard at what black holes are doing. And if we could catch a black hole in the final stages of its Hawking evaporation, for example, we would learn so much from this. Another extremely violent place, of course, is our Big Bang that we heard about. That's why it's very, very interesting to look in more detail than we have so far about what radiation actually came out from the Big Bang, because encoded in that might again be some of the best clues available to answer your questions.
We're running very short of time, and I'm actually going to take the last few minutes to ask a question of each of you here. Now, we've been sort of talking as if everything did start with the Big Bang. We haven't even really talked about the multiverse, and I sort of feel like I'm remiss here.
Yes, we have, just not in this particular universe.
That's pretty good.
So again, I'm going to do a little mini quiz here. Do you think we just have this one universe that started 13.8 billion years ago? Is it your best guess that there are actually other universes, and maybe, you know, there's this whole other question of, you know, getting back to origins, maybe really the origin isn't 13.8 billion years. Max, what's your guess? Do you think there are many universes out there?
Before we talk about other universes, we should probably define what we mean by ours. So when we say our universe, or our observable universe, we don't in physics or astronomy mean everything that exists, because then by definition, we would all have to say no, no, no. We mean simply the spherical region of space from which light has had time to reach us so far, or as Katie called it, the horizon volume. And the question you're asking then is, are there other regions of that same size somewhere else? If space is actually much bigger than the part of space we can see, for example, as Euclid thought, if it goes on forever, then certainly yes. There are lots of other places with other galaxies. Even though we can't see those things
no,
directly.
I'm already defining universe differently than you are.
Just make sure to redefine it before you answer.
But in
Anyway, so I just was going to
universe,
say that
okay.
what's interesting is that, first of all, we have no evidence whatsoever that space ends magically exactly at the edge of what we can see. And in fact, every hour we wait, light reaches us from still farther away. So if you had said yesterday that things end right there, you would have been proven wrong now. But moreover, more seriously, the best theory, the most popular theory we have, what created this space and stretched it out and made it so big, namely inflation, actually predicts that space is vastly bigger than what we can see, so that there is much more. And to me, this is not particularly surprising at all, since we have again and again discovered, as we talked about, that everything we thought existed was part of something even bigger. If a planet, a solar system, a galaxy, our observable universe, so if it happens once again, not such a big deal.
Okay, so yes to the multiverse. Katie?
I'm responding to something that's not exactly this question, but the amount of the part of the universe we can access, the amount of it is going down because the universe is accelerating. So as time goes on, we can see less and less of it. So build your telescopes now. now here's how I would define a universe a little differently. It would be motivated either by inflation or string theory. So I'll talk about the inflation one. So during a very, very early accelerating period of the universe, you can think of a ball rolling down a hill, only in some places in the universe that ball gets kicked back up. So we may be from a part of the universe that rolled down and we got to the bottom, because we have to be at the bottom for us to exist, okay? So that happened here. But somewhere else in a distant region, that ball kept getting kicked up, and maybe when it rolled down at a different time. So this kind of is similar to your definition of a universe.
Actually, yeah. You're talking about what I'm calling the level 2 parallel universes. I was talking about the level 1, and I even talk about 4 kinds in my book for if people want to get really confused. But I'm with you.
So
I'm with you on your level.
These are real physics questions as to whether these things, how different these regions are, and I'm not sure that I'm convinced. Oh no is my answer. I don't know, but I also am not sure I care, because we'll never talk to them. We'll never communicate with them. Those things are so far away that we'll never know about them. And I don't think it's fair to say there's questions about physics we don't have to answer. We can say, well, obviously we don't have to worry about the strength of electromagnetism in this universe because otherwise we wouldn't exist. If it were a little bit different, then your nuclei would fly apart. So, well, we don't have to explain it then because somewhere else they have a different value and humans can't exist. And I'm not satisfied. I want to explain it in our universe now. So, of course there must be other universes, no matter how you define them, but the question is the impact they have on us as physicists, and I don't want their existence to affect the way we think about solving problems within our universe.
Marcelo.
Complicated answer.
Yeah, I don't think this is
question.
a yes or no question. You know, it's kind of unfair to
Yeah,
set
I
it
guess
up
that's
like
right.
that.
I guess that's right.
So you're
That's my
trying to
job
trick
to
us.
ask
Right,
unfair
but
questions.
I'm not going to fall
Instigation.
for this. Because the reason is, Mark said something which we all have experience of. If you're standing at the beach, right, and you see the horizon, where the sky and the ocean touch, you know that that's not the end of the Earth, right? You know it goes on, but you cannot see it. So what you call level one is basically whatever is beyond our observable bubble, because we all live like a fish in a bowl, right? We have this little bubble of information we can cover. The universe will probably continue after that, just like the ocean continues beyond what we see at the beach, right? The horizon line, right? So that's pretty much okay, right? However, the notion of having a multiverse, that is, having not just our bubble universe being the only universe, but having some entity where you have eternally bubbling universes that go into existence and pop up, and some of them grow, others shrink, that is based on extrapolations of current theories that we really can't be sure if they're right or not yet. So if you say, I believe in the multiverse, that is a perfectly subjective statement, but it's not a scientific statement, right? And I think we have to make that differentiation. And the point is, I am sort of agnostic with respect to this. I mean, if there are multiverses there, that's awesome. My main concern is what Katie raised, which is, can we test that hypothesis? And that is a really complicated issue. There are some ideas, actually, a guy from NYU, Matt Kleben, and Anthony Aguirre from Santa Cruz, they have this idea that if there are other universes out there, they may have collided with ours in the past, and that would have left some scar in the radiation that we can see in the sky. So there will be evidence, perhaps, of a past collision with a neighboring
That is the
universe.
only prediction.
That is the only
multiverses.
Well,
that is the best
we can debate
one.
that.
Okay.
And unfortunately, so far, it hasn't really panned out. I mean, people have looked at
stay
the
away from
data,
that
it's
problem.
not working. But even if you do that, right, that means that we may have a neighboring universe. That doesn't mean you have an infinitely huge multiverse out there. One thing is to have a neighbor. The other thing is to have a whole country around you or a whole world around you. So it is a very complicated question from an epistemological point, because we can never be sure that an infinite multiverse exists. In fact, we can never be sure from an experimental perspective that anything infinite exists. Because even if you measure the curvature of space and it looks flat to plus or minus a margin of error, and that plus or minus margin of error, which is how science is done, kills the idea that we can ever be sure that the universe is infinite in the sense as being infinitely flat.
Well, we have many more questions that we could ask, but we have no more time. So thank you all, everyone
In
who
this
came.
universe.
Yeah.
Thank you.
Thank you so much. That was
fun.
That was really